All right, let's just dive right in. Welcome to today's explainer. If you've ever wanted to truly visualize how software is built, and I'm talking going from the tiniest data particles all the way up to towering logical structures, you are in the exact right place. We're going to construct a mental model of C# from the ground up, and we're going to do it in a way that just makes sense.
Here's our roadmap for today. We'll kick things off with a quick welcome to C#, then jump straight into variables and data types, map out logic and conditions, tackle loops and iteration, break down object-oriented programming, and wrap the whole thing up with clean code and compilation. Let's get to it.
Section 1. Welcome to C#, the futuristic safety shield.
So, let's lay down a quick foundational definition. C# is an expressive, evolved, object-oriented programming language. And hey, fun fact, the sharp part actually comes from musical notation, meaning a note is a semitone higher in pitch. Pretty cool, right? Whether you're building massive enterprise software systems, cloud apps, or coding the next big hit video game in Unity, C# is the highly rewarding engine under the hood. It gives us this strict, super robust environment to build our software.
And you know, C# strictness, it's honestly a superpower. Think about languages like JavaScript that rely on runtime checks. With those, the code executes until it literally hits a wall and crashes, like a car that's already driving down the highway. C#, on the other hand, catches errors at compile time. Before your program even gets the chance to run, the compiler steps in like a futuristic safety shield. It checks for syntax issues and type mismatches, basically stopping the crash before you even turn the key.
Moving right along to Section 2, variables and data types, the microscopic building blocks. Okay, so every single variable container in C# needs 3 distinct elements to successfully materialize. You can't just toss your data out into the void and hope for the best. First, you have to specify the type, like an integer, a string, or a boolean. Then you give it a unique name. And finally, you assign it a value. Check out how these specific data types actually look in practice. We've got our integer for whole numbers and our string holding text wrapped in double quotes. But I want you to look closely at the float at the bottom. Notice that F tagged onto the very end of the number? That is a classic quirk of C#'s strict precision rules. If you forget that F, the compiler might assume it's a double and throw one of those compile time errors we just talked about. No way around it. So how do we actually combine these containers? Well, we use string interpolation. By just dropping a $sign at the very beginning of the string, we can elegantly wrap our variable names in curly braces right inside the text itself. It lets us blend these containers into a single, clean line of neon code without having to awkwardly glue things together with clunky plus signs everywhere. It's clean, it's modern, and it's so much easier to read.
Section 3, logic and conditions, branching neon pathways.
This step-by-step conditional logic is what dictates the entire flow of our program. Imagine your code traveling down the if path, but only if the condition evaluates to true. If it doesn't, it pivots, checking the else if alternative. And if all else fails, it just defaults to the else path. Oh, and remember, this is where logical operators really shine. By using the double ampersand for and or double pipes for or, you can group multiple conditions together to build some seriously brilliant decision trees. Section 4, loops and iteration, glowing circular tracks. Visualizing the flow of a while loop reveals something pretty crucial. The program hits the condition diamond first, right? If it's true, it runs the block and loops back around. But, and this is absolutely key, if the condition is false from the very start, it completely bypasses the code. The loop might not run even a single time. And the exact same logic applies to for loops, which are beautifully structured to package the setup, the condition, and the incrementing all into one highly efficient line. Now, here's a massive pitfall to avoid when writing loops. You must never forget to increment your variable. See that arithmetic operator, the x++ inside the curly braces? That adds exactly 1 to x every single time the loop runs. If you forget that one vital little operator, your variable stays exactly the same forever, and your program gets stuck in a catastrophic, infinitely spinning loop. And trust me, nobody wants that.
Section 5, object-oriented programming, blueprints and robots.
This next concept is an absolute game changer because it takes abstract code and transforms it into reality. Think of a class as purely theoretical. It's the blueprint, the literal design on paper. You can't physically interact with it. But the magic happens when you instantiate that class. You create an object. That object is the living, functioning 3D robot assembled directly from those blueprint rules.
To actually build these classes correctly, we lean heavily on the 4 pillars of object-oriented programming: encapsulation, abstraction, inheritance, and polymorphism. Think of these 4 pillars as the fundamental engineering principles that hold up the entire architecture of a robust C# application. They are exactly what allow developers to reuse code and keep incredibly complex systems beautifully organized.
Okay, so what actually goes inside our class blueprint? Basically, 3 main things. First, we have properties. This is where our robot stores its data, things like its name or its color. Second, constructors. These are the initialization instructions that tell the program exactly how to boot up the object. And finally, methods. These are the actions, the input-output machines that let our robot actually do things like speak, move, or calculate math.
Section 6. Clean code and compilation. Best practices. Whenever you're writing methods in classes, always remember the KISS principle. Keep it simple, stupid. If one of your methods pushes past 25 or 30 lines, it probably needs refactoring. If a class inflates to over 400 lines, it's definitely doing way too many things and needs to be split up. Following this ensures your futuristic code structures don't mutate into these massive, unreadable monoliths that just confuse other developers down the line. We want to keep our architectural footprint tight and organized. Look, even the absolute best architects make mistakes. But the beauty is, when your C# compile time shield catches an error, it doesn't just crash and leave you guessing. It gives you exact GPS coordinates to fix the problem. It hands you the precise file name, the exact line number, and even the character position, like line 9, character 7. Then it tosses you a specific error code, like CS0103, which you can easily punch into the documentation to squash that bug instantly.
Which brings us to our conclusion, and honestly, a question that's on pretty much every developer's mind right now. Will C# be replaced by AI in 2026? I want to leave you with a final thought to ponder here. While artificial intelligence is an incredible tool, and yes, it can absolutely assist us in generating boilerplate scripts, human creativity is absolutely essential to design these intricate logical architectures. We are the architects here. Understanding the underlying logic, the object-oriented structures, and those rigorous compile time checks makes C# an incredibly valuable and, frankly, irreplaceable skill for the future. Keep building, keep learning, and we'll see you in the next explainer.